Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, I'm going to be discussing the GIS menu. Up here in HEC HMS, we have a GIS menu, and as you can see, there are most of the options are currently disabled, and that's because I need to select the basin, and then after that, I can select the coordinate system, but nothing much below that. The GIS menu is meant for, among other things, taking terrain data, cleaning it up, and then assisting in a watershed delineation. In the GIS menu, the first option is coordinate system, and this menu system was designed to go one step at a time from top to bottom, sort of as a workflow to guide the user one step at a time to properly delineating their watershed for HMS. Let's start with the first one, coordinate system. So I'm going to go ahead and select the coordinate system. Now there's three ways to actually assign a coordinate system. The first one is by clicking this predefined button, and then I have my choice between the standard hydrologic grid and universal transverse Mercator. If I just select UTM, then I'd have to fill out this data as well. If I select SHG, then that's it. Either way, I just go ahead and click select. And then when I hit the set button here, that basically saves the coordinate system. So if I go back up to coordinate system, you can see that that coordinate system here has been saved. The second option to setting a coordinate system is to browse or navigate to a GIS file that already has a coordinate system referenced, and then that coordinate system will be extracted and used. So an example of that would be clicking on Browse, and then on my desktop here, I have a TIFF file, which we'll be using in this video, and then click Select. Now the coordinate system, WKT, the well-known text, has been added, and then I can go ahead and click Set. Now that's been saved. And then let me go back to coordinate system. The last option here is to actually paste in the actual what's called OGCWKT, the Open Geospatial Consortium well-known text. So let me go ahead and do that as an example. I copied something onto my clipboard and then paste. So this is just a different coordinate system, in which case I can go ahead and click set. Now, we've set the coordinate system, but none of the other values like terrain reconditioning, preprocessing sinks, and so on is available to select. What we need to do now is actually assign a terrain data to our basin that we have selected. So I'm going to go ahead and do that real quick. I'm going to go Components, Terrain Data Manager, and then New. I'm going to call this terrain 1. That's fine. Next. And now I have to select the terrain data file. If you haven't already watched the terrain data tutorial video, then I would recommend you go ahead and check that out as well, because I'm going to skip over a few steps. And here's my project. I'm going to open up the terrain directory within the project, and I'm going to copy in my TIFF file. This is a TIFF file I downloaded from USGS for an area along Central Coast, California. So if you're curious how to do that, go ahead and check out lesson number 6 in this playlist titled Terrain Data. All right, so this is the location. I'm going to go back to HMS and then navigate to that TIFF file. I'm in the project directory here. I'm going to click on Terrain, and here's the TIFF file, and then click Select. And then it is in meters, that's correct, and then Finish. All right, so the next thing I need to do here, I'll close the Terrain Data Manager, go back to HMS, and then with basin selected, I'll come down here to Terrain Data, select Terrain, and then click Save. All right, the terrain has loaded into the main basin model map display here. I'm going to zoom in a little bit. I chuckled a little bit because the projection is off. So we're going to go, or the coordinate system, we're going to go ahead and fix that. So I'll go coordinate system. And I just know from experience, this is UTM and zone 10, Northern Hemisphere, and NAT 83. So I'm going to go ahead and click select and then set. Give it a moment, and that should be corrected. All right, so it's corrected where north is now up and the Pacific Ocean is over here to the west. All right, checking out that terrain data. When we loaded the first terrain, we had our original upload and then the first coordinate system, and then 02 here is the second coordinate system with our .tiff file in the correct orientation. All right, now that would unlock the next few options here on our GIS menu. Let's go with the terrain reconditioning tool. Terrain reconditioning involves cleaning up the elevations in the terrain data to assist with the watershed delineation. Specifically, there's two steps. The first step is building walls, and the second is burning streams. So, what that means is burning walls would oftentimes this step can be skipped because a lot of watersheds will delineate just fine without using this step, just using the basic terrain file. But if the watershed is very flat or you want to ensure a specific delineation, then using this build walls or burn streams option here in within terrain reconditioning may be necessary. So what you would end up doing is navigating to a shapefile here, .shp, which would artificially raise the terrain, and it would be in the shape of a watershed to basically create a wall. And then after that, you would also input these parameters here. The user's manual suggests a 1 or a 2 for smooth raise solve buffer. And it recommends a 100 or larger number for smooth raise height. And there's no recommendation that I read in sharp raise height. But just so you know that the user's manual does a great job explaining the details with diagrams about this terrain reconditioning, both build walls and next is the step 2 burn steps. So I'm not going to belabor that or talk about that anymore here, but just know that this is an option you may need to use for proper watershed delineation. I'm going to go ahead and click cancel, but I will actually use all the other tools in this video. The next is pre-processing sinks. So this is actually running right now. You notice there's a progress bar. There's no dialog box. And boom, automatically it's done. So pre-processing sinks, what that just did was it ran a pit removal algorithm on the terrain data and assigned it to a selected basin model, which produced new hydrologically correct DEM as a raster, indicating the location of the sinks and the depths that the sinks were filled. So in English, that means if we go up to map layers, we can see there's two new layers. First, we had terrain. That was the original terrain data. And now we have a sink fill layer and a sink locations. And you can see those the sink locations on the map in navy blue as I zoom in a little bit here. A number of the GIS processes that we perform will add new layers to the map. So we will be returning to the map layers in just a little bit. The next step is to run the pre-processing drainage. So I'm going to go ahead and run that now. In my experience, preparing for this lesson, this took a lot longer. So I'm just going to let it run and tell you what's happening. It's running an algorithm that will determine the flow direction and flow accumulation for each grid cell in the terrain data raster. So the larger the map you have, the longer these processes are going to take. But what will happen is it will result in a couple new map layers here. One will be for flow direction and the other for flow accumulation. Also, once this status bar or this progress bar is done, we will see a few new records in our terrain 1 directory 02. And you see we already have a new one for the sink, or two new ones for the sink fill. We're going to have a couple more after this pre-process drainage step completes. Okay, so that process took about 10 or 15 minutes. So I thought it might not work, but it did. And we now check map layers, and we see we have two new layers, flow accumulation and flow direction. If we check that terrain directory 02, we now have a TIFF for the flow direction and the flow accumulation. All right, let's go ahead and zoom in just to take a look at we're looking at flow accumulation here. So I believe the value is the number of cells that flows into the current cell. So over here should be like a 1, 2, yeah, very low numbers. But once I hover over the actual stream, we're up to 425, 800. Very cool. Let's go down here and see what this is. 3.2 million. Okay, that's significant. That's very cool. That's part of the watershed delineation process. Also, there is a flow direction layer here that was created here with the different colors indicating direction, I believe. All right, so there's flow accumulation and flow direction. That process drainage step is required to move on to the next step, and that is to identify streams. So when I select identified streams, it's now asking me for the area to define in miles squared. And the default value it provides me here is 100, so 100 miles squared, but I can type in a different number if I want, like a smaller or larger number. It sort of depends on how like coarse or fine I want the resulting layer to be. The user's manual calls this the drainage accumulation threshold that will define where a stream starts. So I'm just going to go with this 100 miles squared value and click OK. And we get another progress bar. And thankfully, it didn't take us long. We have a new layer here called identified streams. And I believe it just coincides with the streams that we're seeing here on the flow accumulation. Okay, so the next one and the last one I'm going to do for this video, I'm going to call this part one, is the breakpoints manager. So up here in the components toolbar, there's this icon. If you can see it, it's like a red dot with a black cross. The label is breakpoint creation tool. This is where we would actually click to create an outlet for our watershed. So if I go up to GIS and then breakpoint manager, you'll see by default there are no breakpoints, and the watershed would start with no breakpoints, or I should say the terrain file that's assigned to this basin. The breakpoint manager will allow you to view, rename, delete, or modify the description of any breakpoints defined in the basin model. By default, a basin model does not contain any breakpoints. At least one breakpoint defining a watershed outlet is necessary in order to perform watershed delineation. Additional breakpoints will force delineation of subbasin elements at that location. So what I'm going to do is close that and then zoom out and then zoom in on the outlet of the entire watershed, which is going to be here is the outlet of the Carmel River. I'm going to turn on the flow accumulation layer as the top layer. That way I can look for a huge number. I'm going to use this cell right here, or maybe this one. Yeah, they're both pretty large. So this is a sufficiently large number to use for my breakpoint. So I'll go ahead and click the breakpoint tool and then click right here and give it a name, breakpoint. I'll call it outlet Carmel River. This probably isn't the exact location, but good enough for a tutorial video. And then click create. Now I have my outlet location here for the Carmel River. If I zoom out on the map, you can see it is located right here on the coast, downstream of all the highlands and the watershed that's flowing to it. So that's enough for this video. I don't want to make these too long, but what we covered were the first 5 or 6 or 7 steps here in the GIS menu in HEC HMS. We loaded up a terrain file, assigned it to a basin, and then went through some of these steps on our way to delineating a watershed.